So let's start with our project presentation. Our topic is wavelet transform and SVD image compression. The aim and the goal of our project is to compare these two widely used, most popular maybe methods of working with image compression, and to check them in some different cases, check how the compressed image looks like when some metrics say that they're the same, and to compare them at all. So let's continue. The wavelet transformation method, actually the wavelet is a function. The function that shows the change of frequency in a time. And it has some wavelets family, but in our project we would use a Haar wavelet family. What is Haar function? Haar function is a function which is equal to 1 when the time is going from 0 to 1/2, and it's equal to -1 when the time is going from 1/2 to 1. Here we can see a formula how we can derive this formula for each mother wavelet, and actually for a Haar one we also can do it. And here we can see a wavelet transformation formula which is coming from an inner product that were covered by our course. So let's talk about the idea of image compression. The idea of image compression using wavelet transform is to represent our given image that is given in a standard basis in another basis which is formed by applying this mother function. And here we give an example for a 2x2 matrices. The idea is if we apply a Haar basis, Haar wavelet function, we want to save some parts of an image, some details. Here we save vertical details, here we save a horizontal one, here the diagonal one. And as you can see, the elements of matrices is lined from 1 to -1. Also, we have a coefficients that one half. That is because we want to work with orthonormal basis. And as we understand, if we apply this, we would get some coefficients near our basis matrix. And actually, the new matrices would be formed by these coefficients. And the idea of compression is to take only the largest one by absolute value, and by this we would apply the compression, because if we save, for example, like 500 of coefficients, the image looks nearly the same as it was before compression. But if we take less, we would save only main details only and ignore the small details, like an SVD. An SVD is strongly covered by our course, so we would not run so deep into it, but the SVD method is, in SVD we try to represent our matrix, our image, as a free matrices that is built on our singular matrix, singular values and singular vectors, left and right singular vectors. And then we would take only the largest one, and because of it we would apply compression. So here we can see that actually it's in some cases it's like an analogy to wavelet method, because in wavelet transformation compression we just take wavelet coefficients, and in SVD compression we just take the biggest singular values. But we would see that actually these methods have a big difference in some cases. So let's move on to the work we have done. First, I want to present a PSNR metric to you. PSNR is a metric which is used on a mean standard error, based on a mean standard error, and it shows us the difference between original image and the compressed image pixel by pixel. what we can see, what is important here, that the PSNR for both images that were compressed by different methods, it's nearly the same. Here we have kept 500 coefficients, and here we have kept 8 most huge eigenvalues. But what we can see, actually the images looks really different. Why is that so? Because the idea of wavelet compression is to save main objects, main edges, and because of it, like our compressed image looks blocky, but an SVD works another way. An SVD save an overall structure, and because of it, image looks sharply, like sharply. And what also is important to say is that, as you can see, in wavelet compression we have many coefficients, and we can work with them. We can take 500 and we can take 499, and the PSNR would change a bit. But if here we got like number of singular values equal to 7, the PSNR would change hugely. So we can say that wavelet compression is more accurate for some kind of works. It might be important. And like for being even more easy to see the difference, we used here the situation that is, I think, not usually used in real life. We take a PSNR that is less than 20. As you can see, in both cases, actually we could not recognize an original image by this image, but still we can see that here we saved 150 coefficients, and here only 4 main eigenvalues, and here the image we can see saves some main singular values, and it looks blocky. And here it's just a sharp image, but we also can see some object, but there is no like some edges in structure. It's sharp at all. So what we are working now is to add another metric, not only PSNR, to check which is even more usable. And also we want to like try to focus on some particular case, maybe where the edge save it's important, it's like significant, to show the difference even more like strongly. Thank you for attention.